Okay, so welcome to the July 23rd General Meeting of the Mount Diablo Astronomical Society. Thank you all for joining. We got a pretty exciting meeting this evening planned, if I can get all my technical buttons working. Okay, just as a reminder, if you still need the announcements to give out for any outreach for the public astronomy nights, I do have a packet up front with those. You can pick those up. Okay, and upcoming star parties. The big one is this upcoming weekend, July 26th to the 27th. We've got the Yosemite Star Party at Glacier Point. Who all's going to that? Okay. Several in-house. Any Zoom members going to that? If you have not yet already arranged with Renee Gandolfi, he's our Yosemite coordinator, please give him an email because we do need to let him know how many people are coming. Oh, we're asking for a head count. How many on Zoom are planning to go? If you guys could raise your hand. Okay. Okay, I have no hand raises. Renee Gandolfi does have a quick announcement. Renee, do you want to have me stop screen sharing and I'll let you take over?
Yeah, that would be great.
Okay. Oh, and my Zoom audio is not coming out, right?
Can do it just on audio. It's a quick announcement.
My apologies, everybody.
That's okay. I've heard from the Park Service. I will hear tomorrow, they promise, whether or not we're going to end up at Bridal Veil or instead we're going to end up at Wawona. I will let everyone know who has signed up. I do need to let the Park Service know that you're coming. And so if you have not signed up yet, please get in touch with me directly so I can get the Park Service the information that they want from us and I can get you a entry pass. Other than that, it looks like today it was only about 95 degrees up there, but it's supposed to cool off. And it looked like it rained up there today, but it looks like by the weekend we'll have clear skies. Thanks, Tara.
All right. Anybody have any questions for Renee? Hold on real quick, Renee. I have a question here.
Renee, when you say get us a park pass, does that mean you're going to email us a pass or they will just have our license plates that we've submitted to you on file?
I will email you a copy of the pass that it's a single sheet of paper and it's signed by the Park Service, if I remember correctly. So you'll actually have it as hard copy.
The first part of what you said didn't come through. Could you please repeat that?
Yeah, I will be sending, if I've got your email and I've got you registered, then I will be sending you the package that gives you all the information and it will include a printed pass for you.
I think he still had a question about the first part. Couldn't hear the first part.
Yeah, we couldn't hear the first part. Could you please say that again?
Yeah. It's if I have your email already registered, then I should have already sent you a package. If I don't have it, it means you weren't registered as of Monday. So get in touch with me directly and I will get you a printed pass.
Thank you.
No, you didn't. That's yours.
Do them all.
Old-fashioned trigger.
Sorry. Okay, we're off to a
Thank you.
rockin' start. Okay. And as a reminder, we've got the Society Observing Night on Saturday, August 3rd, and the Public Astronomy Night on Saturday, August 24th. All the information you need is on our MDAS.net website, so make sure you check that out. Are there any new members in the house tonight? Okay, any new members on Zoom? Raise your hand. All right, so if anybody needs the bathrooms, just a reminder, they're through the doors here. We're going to get started with our What's Up presentation by fellow member Rich Ozer.
All right. So I'm going to have one of those, what I did with my summer vacation presentations. This is not going to be very deep or educational, but it's about this year's Golden State Star Party. Who has no idea what I'm talking about? All right, good. There's at least a few people who have no idea what I'm talking about. So the Golden State Star Party is a big event that we have in Northeast California. Come on. This ain't doing anything.
How come when I checked it 301?
Tech support. All right. You see the little red pointer on the map, and that is the border of Modoc and Lassen counties, and in a little town called Aden, California. If you haven't been up there, all the other towns in the area you'll also have never heard of. So the closest place you might have heard of is Susanville or Alturas, and really there's not much else that makes the news up there. It's as if you carved out a piece of Idaho and dropped it in Northeast California. That's the only way I could possibly describe it. And we've been running a star party there for, a good decade and a half. And we get between 300 and 400 people. This year, it was a little short of that. I'll get into why. Let me see if this works. Thank you. So this is why we picked that location. So I don't know if people have ever seen these dark sky maps before, but you can see where we are is right there in the black. And it's a very dark site. Those are getting harder and harder to come by, especially finding a place where you can drop a couple few hundred people and have a star party. This is what it normally looks like at our site. For those of you who were there this year, this is not what you saw. Usually in the afternoon, we get the thunderheads coming in. It cools off the ground, cools off the air. And this year, that is not what we had at all because we were right under that heat dome that we all suffered with a few weeks ago. So really, this was more the view. And let me play this little quick video here that someone put together. Yeah, that usually takes about 15 minutes. Thank you. So I'll rush through these. So this was more what the skies looked like all the time. And so look, it started off at about 98 degrees and got up to about 106. And that was a little worrisome for me when I saw that forecast coming up because there's nothing worse than people getting sick from heat stroke during an event like this. So I scared the hell out of everybody, and it dropped about a quarter of the attendance as a result. And maybe I still think it was a good idea to scare everybody because we really didn't want anybody passing out or anybody with health problems showing up and discovering that they shouldn't be there. So we had a lighter crowd than we usually do. I think it was about 230 people this year. And instead of the 275 to 300. So I don't know, this is kind of what it looks like during the first day, people driving in, getting set up. I'm just going to go through these slides real quick. And one of the nice things about GSSP is we get some really great sunsets and great panoramas. This is a overhead view from the first day. And you can see that we actually have a space that can easily handle you know, 1,000 people if we wanted to. I think the most we've ever had at the event is about 450. And of course, Mount Shasta has snow again, and I kept staring at that snow. Say, why isn't there any here? This is Andy Albaugh. He's one of the landowners who the family makes their property available to us. They get a piece of the action, of course, but they're, you know, we've managed to form a really great community with the folks up there. It's actually the Star Party's charter, registered with the state of California, is to be building links between rural and urban centers in California. And I think we got the quickest nonprofit status letter that's ever been issued in the state of California at the time that we did it. People would look at me and say, "It took you a month?" You know, and it was like, wow. One of the notable parts of the event are the big Dobs. We had a lot of very notable, serious visual observers at this event. It was started by people who were interested in mainly visual observing before the astrophotography revolution of the last decade. There's somebody familiar, it's Alan. It's not a great picture of him, but it's a great picture of his star structure. And the number of big scopes is kind of astounding. And there's Steve Gottlieb. Many of you know Steve. And Steve has been a speaker here at the club and various places around the Bay Area. And he also has one of these amazing star structure scopes. The guy on the left, Akarsh Simha, is a young man who has been really caught by the visual observing bug. And he has become good friends with three of the most notable visual observers that I know. There's Steve, Howard Banich, and Jimmy Lowry. Jimmy has a personal 40-inch scope in his garage in West Texas. I mean, and these people are like, I don't know how they kept their eyes so good. I mean, I'm lucky to look across the room and see anything, but they're able to, you know, pick out these, you know, faintest of fuzzy objects in these distant galaxy clusters. And Akarsh has jumped on the bandwagon, and he built that scope in 3 weeks. And yes, it had a lot of problems. But we helped him work his way through it. And he also had a real problem keeping his eyepieces clean. It was like he was wondering what this problem was in one of the views. And I said, let's look at your eyepieces. They're all filled with dust. We had a lot of people restoring classic scopes. This is Pete Santangeli. He's on the committee of the GSSP, and he had restored this Celestron wedge scope. And there's more of those. This was one restored by Kevin Medlock, who was set up right next to me. And, you know, those other things in the front, you know, they just started popping up everywhere. And we thought that it was an alien invasion. And then maybe it's a mainland Chinese conspiracy. Yeah, anyway, this was the year of the Sea Star. And a lot of people had those things. And this was one of 3 people from the Tri-Valley Astronomy Club, and they were doing mosaics. And they had this array of telescopes set up, and they were each taking different parts of the mosaic that they wanted to create. So they were being very efficient. Yeah. Oh, there's a familiar face. It looks like you're hot. Where did you go? There you are. Another hot person. I'll just kind of flash through these. This was John Wilson's setup. He was set up right next to me. He had this palatial tent. I believe it had a guest room in it. He brought his C8 with him and is trying to figure out how to do astrophotography. And he was very successful after a lot of cursing. The more cursing than I think John was capable of, actually. And I was set up right behind him there. A much smaller tent, no guest. There's John. And this was, I had to show my rig there. I only show it because I got it to work. And, you know, this is what you see during the day. For those who think about it, they keep their stuff covered so it doesn't get 1,000 degrees. This is this year's t-shirt. Sea stars, sea arp, sea grass. We always have a cow in our shirts. So that's the cow's point of view on the whole thing. It's a cattle ranch. That's why we have a cow. There's Pam. And that's what I looked like after the second day. You know, Mike Lewis is the only person who could pull a practical joke on me from 500 miles away. And this was like planned with like 3 people. The skeleton came from Linden. The shirt Mike had printed up a year ago. It says, "I am not Richard Ozer." And Kevin had collected it all and set it up. The reason he printed up these shirts is that Mike and I, from a distance, look fairly similar. And we're about the same height, and we tend to dress similarly. We both wear a white shirt at the event. And so people were always coming up to him with questions. And if you know Mike, he would not really be appreciative of that. So he ended up printing up shirts that said, "I am not Richard Ozer," so nobody would ask him stuff. Hello. I don't know what that is. There we go. There we go. So we had a great swap meet, and every year we have a great swap meet. A lot of cool stuff this year. Hot stuff this year. There's Mark. This is the 2 kids are the 2 most recent adopted kids who live on the ranch. The Albas adopt their children, and this is their 2nd generation of adoptees. And Chris and Inga, who are there, they own the local store. They come from the Bay Area. They were always involved in the Star Party as part of TAC, and then moved up there and bought Aiden Supply and live there and literally herd cats. Their animals are cats and ducks. So I don't know how that works, but food's a big part of the event. We have good meals. I think this year, everybody outdid themselves. The meals were excellent this year. Food was excellent. I was eating that tri-tip all week. And once it gets dark, you know, you can kind of get a sense of what it's like. It cools off. It starts getting a little more comfortable. Stars come out. This was one of those years where we had a sugary Milky Way. And if you've never seen that, it's awesome. Exactly right. And I'll just we also get beautiful sunsets. And I threw that one in there because you could see the sliver moon there on the right. You can see it right there. It's there too. Yeah, I didn't see that. Yeah, we see the moon. And there we go. But anyway, that's what I'm talking about on the Milky Way. This is not too far from what it looks like naked eye. I mean, it's the Milky Way casts shadows on the ground. I'm going to throw some photographs in. This was taken by Chris Bernardi. And Chris was a friend of Chris Ford's. They both worked together at Pixar. And you guys remember Chris Ford. And Chris Bernardi, as you know, it's a Pixar guy. He knows how to do image processing. This is from Ivor Barker, the Crescent Nebula. Pete took this with that C8 that I showed you earlier. It's the Western Veil. Denny Medlock took this with her sea star. All the Medlocks were doing was playing with sea stars. Kevin tells me, "Oh, I needed a hobby telescope." And of course, Kevin is building the 70-inch, right? And I told him, "You have a hobby telescope." We want him to finish it. Dumbbell Nebula from Diane Martin. Lagoon Nebula from Diane Martin. She sent me a whole bunch. Our own Dan van der Zanden went after the comet with his. Swan Nebula, and Alan Takahashi with his Trifid Nebula photo. You know, when I first met Alan, Paul Zurikowski convinced me that his family owned Takahashi telescopes, and it's like totally untrue, right? But I believed it for like 6 months. Rick Taft, you all know Rick, right? This is beautiful. This is of the Cygnus Wall. And here's one from Mark. Mark, this one was the Lion, right? Lion Nebula. Not Orion, Lion, as in the lion roars. And NGC 6883. And Lagoon? No, Swan.
Come down.
Oh, I already got that one.
Up,
All right, and somebody was having fun with us at the end. 2024, and that's it.
Thank you, Rich.
You want to ask me any questions about the event? See me during the break. You know, we'll do it again next year, and hopefully it won't be as hot. That heat nearly killed me. It's really hard on me to be in those temperatures. But anyway, maybe next year, slightly cooler days and equally dark skies. Thanks for listening.
All right, we're going to take a 10-minute break. We've got refreshments in the back.
Good.
Okay, we're ready to get moving on. So we have our main speaker for the evening, Dr. Frank Marchis. Marchis? I practice so much. Astronomy is a science that inspires everyone, which makes it a great tool for expanding scientific literacy. It also has a uniquely powerful ability to make us aware of Earth's value and fragility. And by inspiring people to engage in citizen science, astronomy fosters not only scientific research, but also collaborative knowledge, building that based on dialogue between experts and amateurs. The Unistellar network is by far the largest network of telescopes and citizen astronomers around the world, with more than 13,000 digital telescopes in more than 50 countries. This network collected more than 4,000 scientific observations in 2022, and our citizen astronomers have helped the NASA TESS mission by confirming exoplanets and supported the NASA DART by recording the impact live and its aftermath, validating the efficacy of the kinetic impactor technique to protect humanity against the threat of asteroid impacts. So we present here some of the key scientific results achieved in 21 to 2024 and future developments in education. So I'd like to welcome Dr. Marchis. He's the Senior Astronomer and Director of Citizen Science at the SETI Institute and Chief Science Operator and Co-founder at Unistellar. He is known for astronomical research. He is published in Nature, Science, and other high-ranking journals, so pay attention. He has had several discoveries, including the first triple asteroid system in 2005, which was named 6639 Marchis in his honor. And since October of 2019, Dr. Marchis has been a member of the IAA SETI Permanent Committee. He has co-authored more than 400 scientific publications, trained numerous students, and served as a science consultant and interviewee for documentaries and movies in English, French, and Spanish. So welcome, Dr. Marchis. Thank you for coming.
Thank you.
Hi, thank you very much, Tara, for the introduction. It was a bit, it's working now? No, it's not working. It's working? I can hear. Okay, good. Okay, so, so today you invited me to talk about citizen science. And I'm gonna mostly focus on the activity we are doing in citizen science at the SETI Institute using the Unistellar telescopes. So who has a Unistellar telescope? Hi. Who has a C-star telescope? Hi. Who has the Celestron, the New Origin Celestron? The? No, the new one, the new digital telescope. No? Okay. All right, so it's good. So I'm gonna introduce what we do with digital telescope first, and then we're gonna go through the citizen science education. So people often ask me, what's the motivation of what we're doing? What motivates me every morning when I wake up to go to my office, to spend my time reading those papers, to write those grants, to manage those people? Well, astronomy always been a true passion for me because I always believe that astronomy are basically, especially astronomers, are basically the people who have always moved the needle into human discoveries. If you look at the history of humanity, you will see that the astronomers, especially in at the Middle Age, starting the Middle Age, they were the one who were kind of challenging the church, challenging the kings and the emperors. They were the one who extend the view of humanity, like extend our thoughts, start thinking about other species living elsewhere in the universe, challenge the way the Bible and other books were basically describing the universe and its formation. So one of the reasons I became an astronomer is because I truly believe that astronomy is the way we can change humanity and make us better species at large. Unfortunately, we know, and you notice that probably as amateur astronomers working in astronomy clubs, that there is less and less people who are interested in the stars and the universe. And one of the reasons is because that's what I call the cosmic blindness. This cosmic blindness is simply the fact that we are illuminating cities and the suburb because we're afraid of the darkness for some reasons. And 90%, 80% of the population live now in the sky, which is extremely bright. So meaning that they don't have the opportunity to see the stars. If you talk to a kid in United States now, less than 10% of kids who are 18 years old or less have seen the Milky Way, which is kind of weird to me because I do remember when I was a kid, the first time I saw the Milky Way, I was probably 6, 7 years old, and someone explained to me that this was basically the age of our galaxy. Seeing the Milky Way made me realize that there was a lot of stars in this universe and there is potentially life there. And that's what motivated me to become an astronomer. I don't want everybody to become an astronomer. Let's be realistic. But I would like people to spend more time looking at the sky, looking at the stars, dreaming about it, thinking about how we're gonna go there, instead of looking at social media and at their belly button and talking endlessly about politics. It would be great if humanity was more inspired by the stars, but what they see and watch on Netflix. So Unistellar was created for that. Unistellar is a company, French-American company. You may have noticed I'm French, by the way, but I'm also American. No? It was not obvious? All right. I can make it very strong if you want. I can speak like that. So Unistellar was started in 2017. I'm not going to tell the story because it will take forever, but we started the story, 4 co-founders, with this idea that we're going to make astronomy accessible for everybody. I'm an astronomer. I'm the only one in the team who was an astronomer. The other one was scientists. And they were very interested in using telescope when they were kids. And they realized that it was very difficult. I mean, you probably remember the first time someone gave you a telescope and you spent hours trying to find Jupiter or Saturn. Maybe the moon was easy, but then planets was difficult. A lot of people never go beyond that. They never managed to see a galaxy and everything. They've never had the opportunity to use fully the telescopes because telescopes are not easy to use, especially in the past. You have to focus, collimate, align. You have to learn the stars, where they're located. Most people don't have the patience or the energy to do that. So Unistellar is proposing to fix this with the first smart robotic digital telescopes. 2017, we did a Kickstarter. We raised $2.2 million. We basically got a higher Kickstarter in Europe. showing that there is an interest. We get 2,200 order of telescopes. And the story was that we were all scientists at the time, and all of us basically quit their job to focus on the company. Yes. Like this? Ah, magic. Okay, now it's better. Thank you. So Unistellar was created in 2017. 2019, we delivered the first telescope, the EVscope 1, then the EVscope 2, the Equinox, which are basically the same model without the eyepiece. And in January, we deliver the Odyssey. This is an Odyssey. This is a new range of telescopes. They're smaller. They can be carried in a backpack like that. And they're controlled with a phone. They align themselves. That's what we call the autonomous field detection. They have a sensor on board, an IMX detector. There is two types of IMX we're using so far, and they provide color images in color. The fact that we released the Odyssey, the reason for which we released the Odyssey is because we learned from our first telescopes. We learned that people don't like to collimate and focus, so we made a telescope that collimate and focus by itself. So this one, you set it up in your backyard. In literally 5 minutes, you observe it. If it's clear, you see stars. That's the condition. And it does work in cities. We basically have an algorithm on board. We call that the deep dark technology that allow you to observe even in cities. Something I want to say, because a lot of people have been asking us that in the past, we don't cheat. We don't generate images. The images you will see with the telescope is truly an image of the photons coming from the photon coming to your telescope. We don't do Samsung. You know the story of Samsung, right? They have a system that if you point the telescope toward the moon, if you point your phone toward the moon, the Samsung phone will know that you're trying to take a picture of the moon, and it will generate an image of the moon. So what you see is not the picture. It's a generated image. And as amateur astronomers noticed that because they noticed that the vibration of the moon was not visible. Sneaky people, sneaky. So we are not sneaky. We are very honest. We are a scientific company. We're really trying to provide the best of astronomy and making people use the telescope and having fun. Is it working now? Because I don't know. Okay, good. Okay, so that was the first thing. We have now more than 15,000 telescopes. I need to update this slide. Sold around the world, and this map here shows you where they are. Most of them are in United States, in Europe, and Japan. But we extended the network with observers in Australia, New Zealand, South America, and we just started delivering telescope more and more in Africa and in some country in Asia. So we're growing the network. So this is what you see. I'm assuming you have seen a sea star in action, some of you. So the Unistellar, I will say it's better, but I'm biased because this is my company, of course. But we basically want people to set up the telescope in 5 minutes and control with the telescope with their phone. They choose a target that the phone will give as a list of potential target observable. The telescope moves to the right location, find the target, and now there is no sound. Sorry. Test. Now it's very low. I have to be like this. Okay. Yeah.
Test. I apologize.
Test. That's better. All right. So now I need to get rid of this. Sorry. Okay. So you see the moon. So what we do stack images using our sensor on board. We analyze the image. We improve the image quality by doing some removing data, which are, for instance, if there is winds or if vibration as well. And we apply some processing like Wiener filtering or deconvolution or things like this that you use in astrophotography to generate an image live. So the goal of Unistellar is to do astrophotography live, basically. You have your telescope, you enjoy observing. In 5 minutes, you see a galaxy, a nebulae, and you don't have to wait 60 minutes to basically get a pretty picture. Of course, the image gets better over time, but most people don't have the patience to wait, especially if you have kids. You probably have noticed they will not wait more than 5 minutes to be able to see a galaxy. Okay, so this is the app. If it's nice later and dark, I may take this one out and we can just use it and I can show you the telescope in action. We also have an app which provides information about the target you're observing. So you learn about the nebula, the Great Nebula of in Orion, for instance. You have some random facts, some more detailed information about the target. So this is some observation you can take with our telescope. Those are relatively old. They was taken with the EVscope 1. We get better now, but I didn't change the slide because I don't want you to focus on the images today. I want you to focus on the science. But this is what you see with our telescope in literally 5-10 minutes. This is 5 minutes of observation with the Whirlpool galaxy from San Francisco. This is the comet Atlas. I think it's also this is from Réunion Island, the southern hemisphere. And this is the Eagle Nebula. You can even see the pillar of creation here. You see in color, and that's something important for most people, because most young people, they grew up seeing pictures from NASA JWST, which are extremely processed, or Hubble Space Telescope. So they expect to see the stars like this. They expect to see the cosmos full of colors, right? And most of the time, in a normal telescope, a classical telescope, you don't see the colors because your eyes is not sensitive at low, in darkness to colors. A telescope like ours provide colors, and that's make a difference. So we have generated we have created a telescope that everybody can use to see galaxy nebulae. But the goal, the SETI Institute where I work, is to have people working mostly in doing scientific observations and developing in outreach and education. So I'm going to give you a few examples of programs we have done so far. So in education, we have been working with the Gordon and Betty Moore Foundation. They make a donation. So we provide telescope for free in community colleges in the US. So you have 50 community colleges now who are using their telescopes with their instructors to learn about astronomy. So they learn about astronomy with their teacher, they do star parties and so on, but they also we also provide educational materials. So they use the telescope to learn what is the difference between different types of stars, what is a globular cluster, et cetera, et cetera. So we're really training the next generation to learn about astronomy. We have done some interesting projects as well locally with Chabot, not far away from here. We have been working with the program called the Galaxy Explorer, where they've identified high school students who are willing to participate to the outreach at Chabot. And 16 of them have got access to some of our telescopes, and they did scientific observation over a week, and they even co-author of papers that we publish based on those observations. So this is a program which has been led by my graduate student, Daniel Peluso, who just got his PhD, in fact, recently. So, today, I don't know why, but nothing works. Okay, hopefully we're gonna have the next slide. Okay, so in the meantime, thank you, Tara. So the SETI Institute is a search for extraterrestrial intelligence in Mountain View, not far away from here. And we are the scientific partner of Unistellar. So what I mean by that is that Unistellar is making telescopes, binoculars, and so on. And SETI Institute is developing the science, the education, and the outreach with those telescopes. I work at both institutions, so that's the reason I have 2 jobs. It doesn't work. Well, sorry. No, I'm not gonna do yet turn off and turn on, but I'm tempted.
Today, I'm claiming the solar flare from earlier.
Close quit, and then out. Yes. Sorry for that.
You're just trying to make me feel better.
You're doing well. Okay. I forgot to mention that. Okay. Let me go back to this. Yeah, so one thing also it's important at Unistellar is that we use, thank you very much, Thomas. So we use our telescope for scientific outreach. Oh, now I need to share it here. We are going to make it, guys. You will bear with us. It's gonna be okay. This is not rocket science, right? Okay. Don't crash on me, you. Yes. Okay. So we do a scientific outreach. So we have ton of outreach programs. We go to amateur astronomer clubs. We do demo. We go to schools. Tonight, half of my team is basically at Stanford University for a star party organized over there. So you do that too, I'm sure. And but SETI Institute and Unistellar are really focusing on that. But something I want to mention, and that's the reason I like this slide, is we also change regularly the software on board the telescope. So when you buy the Unistellar telescope, the first one was capable of doing observation of star galaxy. Then we're starting adding comets, asteroids. And recently, because of the great eclipse in April 2024, we also provided the capability to observe the sun with it. And this is, and we demonstrated this using the great eclipse that we show live to the world. We have more people doing our live than NASA. So just a little moment of pride here. And we have 8 stations distributed along the path. And each of us observed the eclipse at different time. So people could then understand that the shadow is moving along the path and could see also when there is totality, the prominences with our telescope. So we added the capability to observe the sun recently and to observe eclipse as well into our telescope. Today, literally 15 minutes before I arrive here, we announced as well that we have a program to donate telescopes in astronomy clubs around the world. So I just wanted to mention that I'm very happy to see that 4 clubs and university in Ukraine receive our telescope, and they're using them regularly. We also have telescopes in Kosovo and in the southern tip of Brazil. And the reason we're doing this is also because it allows us to extend the network, extend the outreach, and also have young Ukrainian interested by astronomy to still be able to observe the stars. Okay, so the alliance between Unistellar and SETI is dedicated to the science, the citizen science. Citizen science is basically you, anybody who is not a scientist, doing scientific investigation. And I'm going to show you some of the examples and how we do that. So we don't do that alone. We have a lot of partners. We work with NASA on the detection of exoplanets, for instance, Charles University in Prague, in Czechia. We work with the Lucy team of NASA, the Observatoire de Paris. I mean, we have a lot of partners, and those partners basically provide a scientific target to observe. So AVSO, for instance, has been provided some interesting variable stars and to observe that we send to our network. So SETI collect all of this, and we select the one that we consider them feasible with our telescope, knowing its capability, and we send these alerts to you. So if you have a Unistellar telescope, you will receive regularly, I'm supposed to send one tonight, for instance, an alert telling you when there is something interesting in the sky. So tonight, I'm going to send an alert because NASA wants to motivate our citizen astronomer to observe an exoplanet, which has been observed once by TESS and need to be confirmed. And the transit will happen on the 25th of July. So this is the way we do science. I'm gonna skip this because we're short on time. This is the team. I'm not doing this work all by myself, of course. So I have a lot of researchers working here in California, in Georgia, and also engineer working in Chennai, in India, and in Czechia. Ariel Grekowski, you may know her because she's from here. She was born not far away from here. In fact, she mentioned that to me recently. She's our comet lead. So each of us basically are leading one of the scientific effort. So we have Lauren Groh, she's leading the exoplanet. Tom is leading the transient, etc., etc. And we have a dog because if you don't have a dog, you're not normal human, right? Okay, so this is a diagram that shows that you take an observation with a telescope. That after receiving an alert, we make it very easy. Like you don't need to enter coordinate, all of this. Was great in the 70s, but now we don't have to do that. We're using the technology of professional telescopes. You basically have a code, a deep link, we call this. You press a button, the telescope will go to the right location. You press a second button, you have basically the exposure time, the gain, everything, the observation mode defined already by the scientist. And you press another button and the telescope starts recording data. After the data have been recorded, you do some calibration, you know, the dark sky, the flat field. We just do darks for the moment because that's all we need. And then you send the data to us at the SETI, on the SETI server if you want. You can also process them yourself. And what we have, which is not visible in this slide, it's some kind of pipeline which analyzes continuously the flux of data coming to us and sort them out, process them, analyze them, and generate reports. So every morning when I wake up, I can see all the reports of all observations taken regularly by all our citizen astronomers. We have more than 2,200 of them active at the moment. So it's a huge network. And as you can imagine, it's a huge problem to have so much data, so many frames coming every day to our server. So we're working on that, improving this, etc. He did it again. Yeah, I think it's a solar flare. That's the only explanation I have so far. Good, transients. So I'm not going to talk about all the citizen science cases and all the results we have because I will be here for 2 hours, and the last thing you want is to be here with me stuck in this room for 2 hours, right? So we are going to go through a few highlights. Transient, super cool science in my mind. That's something very new. We started that in December last year. The idea is to basically observe flash of light appearing in the sky. They could be nova, supernova, gamma ray bursts, afterglow of gravitational waves, you name it. We have a ton of ideas about where these things come from, how they form. But one of the problems we have is some of them, they appear and they disappear so quickly that we miss it. We basically see one spot and that's all. So we plug our network with large surveys. So we have these professional telescopes like the ZTF in Palomar, which is observing all the sky continuously and generates a long list of transient flash of light appearing in the sky. We receive that, we have an AI that process, analyze those flash, determine whether or not they're new, and if they're observable with the telescope, you get an alert and you can observe them. So we do that with ZTF. You should know, you probably already know, that in next year, we're gonna have the Vera Rubin telescope, which is gonna be doing the same, but the Vera Rubin telescope will observe the southern hemisphere and will basically be way more sensitive than ZTF. So in the future, most astronomers will be continuously looking at this phone to look at an alert, trying to understand what this alert could be. Because it's gonna be, we're gonna get apparently more than 1 million of alerts per year coming from the Vera Rubin about things appearing and disappearing in the sky. So the goal is to build basically a database of light curves to understand what those things are. I'm gonna show you a few concrete examples. So this is the transient, which is a supernova, 2023 IXF. It's a supernova that most of you observed last year, probably. It was in, it appeared in May 2023 in the Pinwheel Galaxy, if I remember, M101. So we sent an alert as soon this supernova was detected by this amateur astronomer in Japan. And this is basically the flux of the supernova has increased. It peaked after 5 days and start decreasing. This is the sample observation of a supernova ever taken. We have 252 observations coming from 115 observers. So these people receive the alert, as I mentioned, and they keep observing M101 continuously. We wrote a paper, and they all co-author of this paper, because that's really the things we do at Unistellar and SETI. We engage the people in citizen science, but we're not using them. We basically allow you to be part of the scientific process by giving you the opportunity to do the observation, do the data processing, and participate to the writing of the paper if you want to. So they're all accepted to be co-author, of course, and we have this beautiful light curve. I know it's just a bunch of dots on the graph, but this is something that is historical in terms of the most sample supernovae, type A supernovae ever seen. And it's a very close supernovae. That's one of the closest of the decade, only 35 million light years. So it's very close to us, right? Something interesting that I wanted to mention is that we also have access to data that people observe. When people observe, sometimes they send us their observation on our server. So the red line here is the detection of the supernovae by the Japanese, the timing of detection of supernovae by the Japanese observer. So what you can see is that we went through our database and we saw before the discovery by the Japanese amateur astronomer, I forgot his name, I'm sorry to call him like that, but we saw basically the supernovae lining up one day before. So this, we truly saw in our database the beginning of the supernova. And this is interesting because people take, professional astronomers, what they do, they take spectrum of this supernovae, and they take spectrum of this here, 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 and here. So what we provide is the context, basically. We tell them when to took the spectrum of this supernovae that was at this moment, and they modelize this, trying to understand how this energetic eruption happened and what type of material is being formed in the core of the supernova. So that's what you can do with this tiny telescope. We do exoplanet transits as well. So you probably already know the first exoplanet was discovered in 1995, roughly. And now we know more than 5,000 of them. And there is more than 4,500 candidates. Candidates are basically planets which has been detecting once or twice by one of the space missions like TESS. TESS observe a patch of the sky, search for variation of light of the stars that infer that there is a planet passing between us and the star, and then move to another location and observe again this patch of the sky. And TESS does that regularly. So that means that when there is a transit of detected, most of the time we don't have TESS to observe it again. So we need some other telescopes to do that. So this is the goal of our program with NASA, is to help confirm newly discovered exoplanets by TESS, and to also refine the timing of those exoplanet orbits. How much time do I have? I have no idea how long I've been talking. I'm so sorry. Okay, good. So what I meant by that is that we detect a planet candidate, send us we have access to the database, and we basically curate this database, finding the one that we can observe with our telescope. We send an alert to you, you observe this exoplanet. If you detect this exoplanet, we confirm its existence, and if we had multiple observations, we also refine the orbit of this exoplanet. So we know now the distance of the planet to the star, and we know if the planet has some perturbation due to presence of moons rings, or maybe the presence of another exoplanet nearby. I don't know for you, but when I say that, and every time I say it in my speech, I think it's amazing that in 2024, we are capable of detecting, analyzing the light, and confirming the existence of an exoplanet in orbit around another star with a small telescope like that. The technology advanced so much that now, with a telescope which costs less than $2,000, you can confirm the existence of an exoplanet. And probably some of you remember in the 90s, most astronomers will tell you, no, there is no such thing as exoplanets because we've never seen any. And now we know them, and now we can characterize them in our backyard. So I think it's extraordinary we can do that. And because I know you want to, okay to believe me, but you want to see some example, here are some examples. So that's one of the first one we observed, that WASP 50b. The name of the exoplanets are awful, so bear with me. I'm not the one who decided that. So this is from the survey WASP. And what you can see here is the flux of the star and a drop due to the fact that there is a shadow of the planet passing between the star, the host star, and the planet. And from the shadow, the profile of the shadow, the profile of the attenuation here, we can estimate the timing, the location, and the orbit of the exoplanet. So this is what we generate using the data coming from our network. So if you do an observation, the goal is that in less than 24 hours, you receive the light curve of your observation. And you will clearly know whether or not you detected this exoplanet. This is a very cool example that I like, because this was done by our citizen astronomers, one Bruno, located in Caen, Normandy in France, and Justus, located in Georgia, Athens. And they talk to each other on Slack, because that's the way we interact with, between each other. And they discover that there will be a potential transit of an exoplanet called TOI 2031.01. It's a candidate. What happened is that Bruno observed it first here. And then when the sunrise in France, Justus took over and observed the second part of the transit. So combining the observation, they have a complete coverage of the transit, and they confirm the existence of this exoplanet. It's one of the first exoplanet of TESS for which we confirm the existence. This is super new. I think that was like, that was not today. That was published like a week ago. This is the paper that was published in Astronomical Journal. It's a exoplanet called TIC 39381A343b. You will remember this one, I'm sure, tomorrow when someone will ask you, what did you learn last night? So we can see the profile of the attenuation, the transit here. And the reason this was kind of a cool result is because it's a very weird exoplanet. It's what we call a warm Jupiter. It has an extremely eccentric orbit. It's orbiting 15 AU from its star. So we think that what we're seeing here, it's an exoplanet which is in transition. It's going from being a distant exoplanet to a close exoplanet, a very hot Jupiter. So it's a ton of theory about how those things forms, how they involve, what happened exactly in the dynamic of this. I'm not going to bore you to that. But what is important here is that those observations was done by 4 Unistellar observer. Yes, there was questions or comments? Or just someone speaking? No? Okay. Okay, planetary defense, another project we do. The goal is to protect the planet. Yes. Let's protect the planet against asteroid impact. How we do that? Well, by observing and searching those asteroids, because you know that Earth is not alone in the solar system, right? There is all these other planets, the sun, but there is also a lot of small fragments, remnants of the formation of the solar system that we call asteroids. And they're very interesting, those asteroids, because they have different shape, size, constitution, We now have close-up of those asteroids. We see them, they're rubble pie, some of coherent. We see that they have some kind of activity. They're way more complex than we imaging in the past. We used to call asteroid flying rocks because we thought they were like stupid piece of rocks that were orbiting describing a Keplerian motion around the sun. But now we know that they're super interesting. We know that they can have babies because they can spin so fast. They can start ejecting material and this become a binary. And sometimes the binary matures so much that after a few 100 million years, they split. And the binary, the baby, become another small asteroid that take his independence and go to another orbit. So we see that in the solar system. And it's great, but it's very complex now because we know that the orbit of those asteroids is not purely Keplerian. So they can change over time. So that's why we need to observe them regularly. Every day, astronomers observe more than 2,000 near-Earth asteroids to make sure that we understand their orbit and how it evolves with time. So when you observe with our telescope, you see this kind of things. Let me see if this is a movie. No, it's not a movie. So this is basically, it's very small, I'm so sorry. But if you look very close, you see this tiny line here? That's an asteroid. That's the asteroid Isabella. It's a main belt asteroid. And normally, yes, if you click here, sorry, that was you managed to do it? Yes, you can see it moving. So that's the asteroid moving with respect to the stars. What you have here, it's what we call a Lie curve. So an asteroid is not perfectly spherical. It has this kind of elongated shape. So what we do with the unistellar network, we analyze the light of the asteroid. The reflected light depends on the shape of the asteroid. And from this, we derive the spin of the asteroid, and we have an idea of its shape. And that's important because the shape of an asteroid gives us direct indication about its formation and its evolution over time. So this is the asteroid 1999 AP10, another great, beautiful name. I tried to name those, though. This is one of the things I tried to do. But this one I did not. I tried to name it after an amateur astronomer in Mexico, but they refused for some reason the name. So anyway, so 1999 AP10 was observed in 2020 by more than 26 citizen astronomers, and we get a lot of Lie curves, okay? And using numerical modeling, we derive the shape of this asteroid. And that's the first time we have the shape of this one. What does it matter to know the shape of a rock? Well, from the shape, we derive basically the evolution, where the rock comes from. We can see, for instance, you have the top shape, it will be made of rubble pie. Or if you have a very irregular shape, it will be probably a rock, like a coherent rock. And this is important because if one day we have one of these asteroids that impact our planet and we want to deflect it, we need to know in advance what it's made of. A cool result we did in 2022 is to survey the DART impact. So NASA got funding to crash a spacecraft on the moon of Didymos called Dimorphos. And this is the last images we got from this spacecraft. So you see the spacecraft coming close to the moon and crashing into it. And that's all. So what we did, we alerted our users in the southern part of Africa, because that's where it was visible. That's where the impact was observable. And we have multiple observers. We have people in Kenya. Susan Murabana was one of our telescope, did a star party, and they observed the event live from Kenya. And we also have people in Réunion Island, close to Madagascar, and southern part of Africa again, who observed this event. And this is what they saw. And if you want to have a laugh, just watch the live we did, because we did a live of this event. And you will see that for the first time, I kind of could not find anything to say because I was so impressed. So here what we saw. So this is the path of the explosion. So what basically happened here is that a lot of material got ejected So this is the asteroid itself. And in fact, there is two asteroids in study dot here. There is a 400-meter asteroid and a 100-meter asteroid. We don't see that because we don't have the resolution for it. But when the asteroid is moving with respect to the stars, and when the explosion, when the impact happened, you see a lot of material. Again, is doing this. A lot of material being ejected from this asteroid, from the moon of the asteroid. So what does it matter? Well, it matters because hopefully this will unlock and I will be able to show you. But what we did, we realized quickly that we created a comet here. Humanity created a comet. Ariel Gakowski has been doing all her career in studying comets. So skipping the details, assuming that we created a comet, the composition of the dust, the size of the grain, the illumination, etc., she could calculate, she managed to calculate the amount of energy sent to this asteroid. And she realized that the energy was so important that this asteroid orbit was basically modified by the impact. We published this in Nature, which is one of the major journals in the scientific world. And interestingly, we have 3 papers coming almost at the same time who also confirm our calculation. One from NASA, from the spacecraft, and 2 others from telescopes like JWST and so on. But what is interesting is that we are the only telescope that published the impact live. Nobody else have seen it. JWST missed it. Hubble Space Telescope missed it. Don't ask me why, but it's always a funny story. And but we managed to do it. JWST there was some issue with the timing apparently, and the Hubble Space Telescope was on the other side of Earth, so he could not see it. But because, yeah, I'm trying. That's I have my wheel of death right now happening. Sorry. So I'm gonna do again my master reset. This is weird. Never had problem with my mic.
It's my fault. It has to be.
I cannot even take it. Okay. Come on.
I'm just gonna see is that the issue? No.
Okay, I may have to turn it off completely then. Yeah, but then I have to restart everything to move the. Don't do that. Yeah. Yeah, but
We have a frozen computer.
Is that an Apple? Yeah. Yeah.
So we can't blame the Microsoft issue either. Control delete, yeah.
I don't have the antivirus brought something, don't worry. Well, I can tell you what happened last Saturday. Friday, I left San Francisco for Sedona to install a station, a laser city station. So we landed there. We waited for a colleague. She was 4 hours late. She got 2 hours to get the suitcases. We went to a store. We could not buy anything. I rented an electrical car. None of the electrical station was working. It was it was like zombie apocalypse, basically. And then all the restaurants were closed because we left Phoenix late. And we found a gas station. Say, oh, great, gas station. I'm sure they have food. We arrived there. We could not pay with our credit cards because they didn't have network. So I basically survived on a tiny box of Springer like this for the rest of the evening. Yeah.
My fault too.
Okay.
I'm so sorry.
It's okay. It's funny. It just reminds us how we depend on technology way too much.
Oh.
Ah, no?
No.
Okay. You know what? I have to do it. Master reset. I will start quickly and I will continue to speak. Sorry. Okay, so we did this. While he's rebooting, I'm gonna basically talk about the rest. So this was one of the major results of Unistellar because, as I mentioned, we were the only only telescope that truly managed to observe this impact. The only thing we do, we observe comets. So comets are great. We observe comets with a telescope probably often, right? And there is a lot of them. There is like more than 100 of them every year observable with a small telescope like that. To enter into technical details with our telescope, we can reach magnitude 17.5. Yeah, I need to, he needs to go back to my desktop, etc. We can go to magnitude 17.5, so it's quite faint. We could detect, for instance, the comet 2023 A3 Chuchin-Chan Atlas, just when it was detected. So with our telescope, you can detect comets when they're extremely far away from us. And what we're trying to do is to follow those comets as they come closer to the sun, because their activity depends on the distance to the sun. And are we done? Yes. Okay. And the distance to the sun and their composition. You probably heard a lot that, oh, this is going to be the comet of the decade. And then yeah, nothing happened, right? You all have examples about this. But well, we're trying to avoid this by following those comets as they come closer to the sun. And this way we can confirm whether or not they're going to be the comet of the decade. So for your information, 2023 A3 Chuchin-Chan Atlas, that people claim will be the comet of the decade in October, is probably not going to be the comet of the decade. But there is still, so the reason it's not going to be the comet of the decade is because he has a lot of dust in his interior, more than other comets. It's a very dusty comet. We don't know why. Some of them are dustier than others. However, because it's very dusty, it may have what we call a phase effect, and we did not yet publish that. We're working on this, which is going to make it extremely bright, but for a very short period of time, like less than 3 days. So the take on this comet is that we're going to publish the light curve that we have derived from this idea that it's a very dusty comet, and hopefully you will see that it's going to brighten and then disappear very quickly. It will survive the perihelion if everything goes right. Okay, I have everything but the zoom. So let me just start the zoom and we back to this. Sorry. I have the feeling I'm come on. No audio. Okay. You good? We see it now, right? Okay. I just want to go full screen and we are done. Okay, you wanted to see that again?
Yeah.
Here we are. Much nicer now, in fact. I should have rebooted my computer before. Okay, so this was very impressive. And something you don't see on this animation that I saw live is that also the color change. It become extremely yellowish orange, implying that we have very thin particles of material ejected. So this is the confirmation. This light curve here is basically the light curve of the flux. So it's 14.5 magnitude before the impact. Suddenly the impact happened. So we timed the impact exactly. We get the same numbers that NASA published. And then a quick decrease. And then later on, the cloud of particles also starts scattering. And if you could follow this graphic, start decreasing slowly. For over 3-4 months, we basically we could measure the activity. We have observers from everywhere in the world. I like this map. So you know I'm French, but I'm not really French. I'm from Réunion Island, in fact. It's an island like Hawaii. It's part of France.
but people over there like me. That's my proud to have that people in Réunion Island detected this event and we published in Nature. We have observers from everywhere in the world that observed before and after, 31 citizen scientists, and 4 observe it live. And we published in Nature again, so that was kind of a big success for the network. So comets, I already mentioned what we do comets. I show you some observation of comet. That's an observation from Scott Gardner of the comet E3 ZTF. You can see the dusty part of the comet, so the coma and the tail, the dusty tail. And if you look carefully, you can also see the magma tail, which is basically in the radially radial direction of the sun, and this is ionized particles that interact with the magnetic field of the solar wind. Comets are cool, but they're so complicated. They're never really the way we want them to be, and they always surprise us. So these are another comets at 12 ppons. You probably observed that. This one, it was very bright this year in spring. This is Anushka observation in France. I forgot to take this one, but you can see the central tail, so which is the magma tail basically, because the sun is exactly in this direction here, and you can see the coma, which is beautiful. I mean, this comet has been was an amazing show for our astronomers. And as I say, there is comets every night. You can observe with a telescope. So sensitive that you can observe them every night. We will observe another type of comet. So this is the figures that I mentioned to you. So this is A3, but that's the one we not yet published, the one I just mentioned. But what is interesting is that we can combine all the observation of the comet by our observers. That's this tiny dot you see here. And these are the name of the people. We keep track of that. So they observe in April, that's December, sorry. November, December, and that's March, April, and so on. And at the time, we noticed that there was a small attenuation. This line here is basically the theoretical activity of the comet that we modelize, assuming the size of the particle, the type of activity that comets generally have, and we saw this decrease. We confirm this decrease is going to be published probably next week. It's even getting worse and worse. And that implies that this comet doesn't have the same behavior than the other one. It's very dusty. But, as I mentioned, it's not going to peak at 0 magnitude, like the same magnitude than Vega. It will basically have this very complex light curve, where it's going to be slow, 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 and then suddenly have a peak when they have a very specific orientation and then decrease. We will tell you that when the peak of X will happen, you will take your telescope out and you will be able to see this comet brightening. Okay, some cool stuff we have done is to observe missions on Earth taking off. People ask, can you observe during the day? So yeah, you can. And in fact, we went to Vandenberg and we observed the launch of a SpaceX mission, Falcon 9 mission, with our telescope. So you have an idea of what kind of quality. We were 3 miles away from the launch pad at this moment. But we also observe things in space, like artificial objects. So we observe JWST being launched and separated from its booster. We observe JWST all the way to the Lagrange point. And we also see the light curve of JWST due to the fact that it was rotating on 16.5 hours. We also saw the deployment of the panels of JWST. This is a paper that we published just shortly after his launch. So this is the kind of stuff you can do with our telescope, and that's campaigns that we create to engage the people. I mean, it's super cool to see a JWST on its way to the Lagrange point. I mean, come on. But it's super easy to do that because we calculate the ephemeris for you in advance. We send basically, we develop tools which are as simple as possible. You detect your location, and from your location, provide the ephemeris, the position of the object, so you find it in the sky. So citizen science, how many much? 5 minutes. Citizen science is not anecdotal for Unistellar. It's truly our DNA. We have more than 4,000 observations collected in 2023 with our telescope. So it's very like we get a lot of observation. Too much that we cannot even publish everything. But something we do is that if you don't publish them directly in scientific paper, we make them available to the professional community. Meaning that if you observe an asteroid, the location in the sky of the asteroid and its brightness will be in the MPC database. So professional astronomers use this regularly to recalculate orbit of asteroid. If you observe a transiting exoplanet and you detect transit, we put this database in AAVSO database. So some professional astronomers may use them in the future. So we're not wasting your time. We truly make sure that the data you take will be somewhere in the database. So maybe in thousands of years, an astronomer of the future will use the data to refine the orbit of an asteroid or to refine the orbit of an exoplanet. What I will finish is that we believe that we're creating something new, a new astronomy. Astronomers used to be kind of, in the Western world specifically, astrologer. There was a few of them working with kings and emperors and telling them the future as an excuse for them to observe the stars. Then in the 70s, we have the second revolution where we started observing, exploring the solar system. And there is still a few number of astronomers. 2000, in these decades, we have an increase of the number of astronomers because of the exoplanet revolution. The fact that we discover all these worlds in our galaxy that could potentially be habitable and maybe one day we find life. So what we're doing now, we're doing this new astronomy. And this new astronomy is for us, the idea is to engage the people in doing astronomy. So when I say doing astronomy, is that spending time outside in the outdoor or with their friends, their family, and observing the sky, the galaxy, the nebulae, the comets, talking about it, spending some time also collecting data and learning about the universe. Again, the goal of Unistellar always been to democratize astronomy, to make astronomy accessible and fun, so people spend more time looking up and less time looking down. And I think we have succeeded somehow, but you're more than welcome to join the family. And I would like to say that you don't have to have a unistellar telescope to do the citizen science we're doing. You can have access to all the information, the target we're observing, the campaigns we're doing with normal telescopes. So you can know what comet to observe tonight using our tools. We don't do tools only for our telescopes. The goal is really to make astronomy accessible to everybody who has a telescope and want to use it. And I will finish it with this, saying that we are working on expanding the network. If you have ideas, if you have a community college you think should have a telescope, if you have a museum or you work in a specific area, you want our telescope to be part of the place, let me know. We are creating new science projects, campaigns. One's going to be released very soon, satellite constellations. We're going to need a lot of you to observe the satellites and to map them, to know where they are, to know their brightness. So if you have a telescope, again, join our campaigns and observe satellites for us. It's going to be cool to be able to know where they are and finding, for instance, where we have to turn off the Vera Rubin detector so it's not affected by a trail of Starlink constellations. And part of developing the network is to make the science easier and to have more public engagement, translating the app in multiple languages. So we're working on that and more partnership. And that's all. Thank you very much.
Thank you, Dr. Marchis. We have 5 minutes for questions. Does anybody have any questions?
One question here.
Organization again, it's not Unistellar.
SETI. Search for Terrestrial Intelligence.
You work for SETI?
Yeah.
The SETI. Okay.
Yeah.
So SETI's partnering with Unistellar?
Yeah, we are the scientific institution of Unistellar.
Okay, but SETI search for extraterrestrial.
That's a good question.
It's a
Was-
different SETI?
No, it's the same, SETI.
Yeah.
So SETI search for extraterrestrial intelligence, but most people know us for the radar, from the antenna
Paris,
survey,
yeah.
but we do more than that. We do search for life elsewhere. Formation of planetary system is part of it. Understanding, for instance, how many planetary systems have Jupiter and Saturn-sized exoplanet. It's extremely important. So that's the reason SETI is interested into the research of Unistellar.
Sure. Thanks for
There is, and we also, something I don't say, that David, you see that I mentioned SETI here? We are just putting together a survey, an array of small telescopes that will be observing the sky 24/7 to detect laser pulses from extraterrestrial civilization if they exist. So they will basically, this instrument will tell us if there is a flash of light coming from this civilization, a laser. And guess what we'll be able to observe continuously those lasers, these telescopes. So we are part of the SETI research as well. We're working on that, in fact.
Any other questions?
Thank you. I'm interested in how you do the data reduction for the light curves. And does each telescope generate its own light curve and then they're transmitted to a central database?
So the telescopes don't make their own analysis. So the telescope send to us FITS file. Can I be technical? Yeah. FITS file, or TIFF sometimes, we can decide, but we use FITS, astronomers, professional astronomers. And then the FITS file, when they reach our server, they've been tagged. So we know if they're coming from people who wants to do science, because we have a science tag associated to each file. Then we classify them in different type of science. And from there, we decide the type of processing we do. So photometry is done using aperture photometry and comparing with catalogs surrounding stars. We do astrometry by the same using catalogs of Gaia or something like that. And the sensor is a RGB sensor, it's a Bayer matrix sensor. So we have an algorithm that monochromonize, I'm not sure it's a real word, but basically make the light curves not sensitive to the color of the object. Thank you.
Anyone else? Okay, and I don't have any questions from the Zoom audience either. Thank you very much. Thank you all for coming. And thank you for tolerating the solar flare interruptions. I feel like I'm getting close with the audio, which, and then all my Zoom settings had reset somehow. So I will work on all that, and we'll see you guys next month. Thank you.
So that light curve thing, data analysis,
Which one?
the last question.
Oh, the way we do the analysis?